Hello, so we are back again in our plasma class. So today, as we promised in our previous class, that we will be studying the plasma kinetics, and under that we will be studying orbit theory, kinetic theory, and fluid model. Only the basics will not enter into uh, much detail of this kinetic theory and fluid model. We'll do all the elementary knowledge that is required to understand our devices. But these theories are quite involved, and entire course can be taken on this kinetic theory or this fluid model. I'll not go into all those things, but the basic machinery that you will require to understand your device, the behavior of your device, will be covered in this class. So, as we are talking that plasma kinetics can be handled in three different ways. One is orbit theory, and the other is kinetic theory, and then fluid model. So, each of these theories have some region of applicability. So when you are talking about the orbit theory, it is applicable when collision between particles are less frequent. It focuses on the trajectory of the individual electrons or ions under the electric and magnetic fields. Then it completely neglects the collective behavior of the plasma or the collisions. You know that as if all the particles are independently reacting on the applied electric and magnetic fields. They are not influenced by each other in this orbit theory. And if so, then where it is applicable, when the collisions are less, as I told you, and this gives us lots of insight about the particle kinetics and the particle behavior inside a device. I'll come across this in this class. So next comes the kinetic theory. So in this kinetic theory, it is basically an exact description of the kinetics of the particles contained within a plasma. Here, each charged particle evolves under the Newton Lorentz force equations along with Maxwell's equations under your strongly and rapidly varying microscopic field resulting from the superimposed your external field and a self-consistent field generated within the plasma by the other charged particles. So that is why it is an exact description of the plasma. So it gives the exact microscopic description and ensembled average kinetic description in the 6 plus 1 dimensional space. So what do you come to know? At every instant of time, the plus 1 dimension 1 is for the time, and the other 6 dimensions are basically for 3 is for space xyz, and 3 is for other 3 are for velocity components, 3 components of velocity. So that is why 3 for space, 3 for velocity, and 1 for time. That is 6 plus 1 dimension state space. And here we describe every species position and momentum at every moment. Sometimes we are getting information more than what we require, so people goes for ensemble average things or time average things. You know from your statistical mechanics classes that time average and ensemble average basically leads to same thing, same final results. Now here we'll try to get some flavor of that ensemble averaged and behavior of systems. Will come across this plasma kinetic equation, Blasov equation, and then that how to simplify them, and we will go for this average behavior, ensemble average behavior, and whether we can solve the plasma kinetic equation, how we can handle the collisions, and then from that kinetic theory, whether we can reach some solution, we will get that some Langmuir waves, electrostatic waves that can be supported by the plasma, and what may be their dispersion relations. We will learn all these things in the kinetic theory. So that will actually suffice for understanding behavior from the common plasma devices that we come across in our laboratory or in the processing plasmas. And then we'll come to the fluid model, where we'll see that kinetic theory definitely gives some exact description, but sometimes handling so many equations together becomes really problematic, even with the greatest advent of computation power in present days. So what we'll do actually, we'll integrate our the velocity space. Like suppose we have a glass of water, and there are so many molecules inside that, it may be of the order of say 10 to the power 27 molecules per meter cube kind of thing, and there we may not be interested in which molecule is moving at what speed inside the glass. Rather, we are interested, if you want to drink the water, we would like to know how much volume of water is there inside the glass, so that I can say drink a 500 ml of water if I am thirsty. So like that, we are not bothered about the velocity of each and individual this water molecule inside the glass. But of course, we won't like that the water spills on my shirt, right? So that is something, the fluid as a whole is moving, and there are something where the individual molecules inside the liquid water, they are moving. So essentially what we are doing, we are getting into a formalism where we are integrating over the velocity space. Like the water molecule may have velocity from 0 to say infinity anywhere. Now we are not bothered about that. We want to know how much of how many total number of molecules are there present inside the glass. So what we'll do, we'll integrate over the velocity. So what will result? You are basically arriving from 6 plus 1 dimensional state space to 3 plus 1 dimensional physical space. So what we have done, you have integrated over the velocity in the fluid model. So you have lost all velocity information. Now what you are left with is the physical space, x, y, z, and time. Okay, and that is the space where we are very much comfortable, and every day where we deal with. So those things we can easily handle, and we are very much comfortable. So we'll start from the orbit theory, then get into the kinetic theory, then get into the fluid model. We'll know the basic mechanism, how to handle a plasma system using these models, what essential and basic information we can extract out of these theories, which will make us competent to deal with any laboratory or processing plasmas, cold or thermal or non-thermal plasma that we are going to handle in this course. Okay, so we start with our orbit theory. So what we'll deal here is the motion of individual charged particle in presence of electric and magnetic field. Of course, we will have the freedom to shape the field configuration. So such studies are very fundamental to several important applications, like say particle accelerators, then magnetic mirror configuration, drifting of charged particles inside a device. To understand the behavior, this simple theory will help us a lot, and we assume that the prescribed field, what we have applied there, they remain unaffected by the charged particles. So this is a basic assumption that whatever field we have applied, they are not getting influenced by these charged particles that we are, whose motion we are trying to understand. So the first case we come under the orbit theory is that some magnetic field is applied but electric field is zero. Okay. We know that the charged particle is basically governed by the Lorentz force equation, which is nothing but force is equal to charge into electric field plus Q is the charge into V cross B. This Q V cross B is a very interesting term in the electrodynamics. You know, it links the velocity with the electromagnetic fields. So this is a very interesting, and I'll say it is of immense significance that when a charged particle at rest, magnetic field will not do anything with that. But the moment it try to move in any direction, it will apply force B cross B, and most of the time it will try to make the charged particle rotate around the magnetic field. So what we are starting in this case, in this present case, we are assuming that E equal to 0. So in the Lorentz force equation, you just put E equal to 0, what you will get? You will get Q V cross B. So that is the motion. Since V cross B is acting in a direction which is always perpendicular to the magnetic field, and so this V cross B in a direction which is perpendicular to both V and B. Okay. So now this work done is the displacement along the direction of force, and this V cross B, what it is doing is force is making a movement in a direction which is not in the direction of the applied force, this B actually. So see, that is why in the direction of B also, neither it is in the direction of B. So in the direction of V, it is not applying any force. Okay. So that is why the kinetic energy of the charged particle, that is half mv square, it remains constant when you have applied no electric field. So as long as electric field is not there, its kinetic energy will remain constant when you apply a magnetic field. So this kinetic energy is constant is an important property for motion under the electric field. Motion under magnetic field when the electric field is 0. Now when the motion, as I told you, F is equal to Q V cross B. Okay. And the particle is rotating. You have already done this in your higher secondary course, that you can equate it with your centripetal force mv square by r, and you can get the radius of gyration r equal to mv by b into q. So what is that? This is inversely proportional to the magnetic field, and it is proportional to the velocity. So what is the radius? The radius becomes more when your velocity is more for a given magnetic field, but for a given velocity, if you are increasing the magnetic field, it will rotate in a tighter and tighter orbit. Okay, because B increases, R decreases. So you are getting the radius reduced. So center of the orbit of gyration is called the guiding center. Just this is some terminology. And because the total energy is constant, so rotational kinetic energy half mv perpendicular square. V perpendicular is the velocity component in direction perpendicular to the magnetic field. So this is the orbital motion, and that is equal to k minus k parallel. K parallel is your horizontal motion, and that is not getting influenced, actually unaffected motion of the particle in the direction parallel to the field. And this V parallel is not at all affected because no force is applied in the direction of the V parallel, because of the essential fact that V cross B has no component in the direction of B. So it is always perpendicular to that. So that is why some unaffected motion in the direction parallel to the field, that is V parallel, and perpendicular motion, which is described by half mv perpendicular square as the energy, the rotational kinetic energy. Now, we'll now define one important thing, that is magnetic moment. It's very important to know this thing at this point, because we'll use this expression later on to understand many other aspects of charged particles under a given magnetic and electric field configuration. So, that magnetic moment is defined as the current into area. What is the current? Current is charge into frequency. What is the frequency? This is equal to nothing but v perpendicular is the velocity per second, how much length it covers in the orbit, and this is divided by 2 pi RL is the basically your perimeter of that circle. So if you divide, then how many rotations it has made per second, that is known. So that is nothing but the frequency. Charge into frequency gives you the current, and then when you multiply the current by the area of the orbit, that is pi RL square, then you get the magnetic moment. So you just simplify this and you get this as, you see that we have written it as q v perpendicular RL by 2 after simplification. And what we have done, this RL we already got in the last this thing is equal to mb by bq. So b is here the v perpendicular and b is bz basically. So this we have just put that value over for RL over here, mb perpendicular bq, and what we are getting, you see, half mv perpendicular square, and q get cancelled. So what you get? K perpendicular I bz. So from this actually we find that when the particle orbits under an electric field, under a magnetic field without any electric field, then the motion is just F is equal to qv cross b, and the magnetic moment of the orbit is k perpendicular by bz. So what we should note here, you just note that when you are getting an expression of the type F equal to qv cross b, then you must be sure that it is an orbital motion. Whenever some such equation appears, F equal to qv cross b, for the motion of charged particles, you must be sure that it is an orbital motion of the charged particle q with a velocity b and in a direction perpendicular to b. So with a velocity v perpendicular, it will just rotate, and then you will get an equation of motion of this kind. So in later on, actually, whenever we come across any equation of this type, we will say that this is a purely orbital motion. Now next we come the case when there is a uniform electric field E and a magnetic field B, but E and B are perpendicular to each other. Okay, so E and B are perpendicular to each other. So orbit of the charged particle governed by the Lorentz force equation F equal to q E plus B cross B, as usual, the Lorentz force equation. Now here we'll try to get some insight about the motion under this electric and magnetic field. So this is a very peculiar kind of motion. Usually what people think, what any student or typically when I ask a student replies that the charged particle will rotate because of this v cross b motion, and then it will be drifted along the electric field E. So what their answer usually remains that the charged particle will move along the direction of E and they will be pitching with some pitch, and they will make a rotational behavior, but the drift will be in the direction of E. But this is actually not the case. This is actually not the case. That is why I will tell you this kind of motion is particularly known in plasma as E cross B drift motion. And whenever I am saying E cross B, you can understand the motion is in a direction which is perpendicular to both E and B. It is neither in the direction of E nor in the direction of B, it is in a direction perpendicular to both E and B. Okay, so we'll just make a little small derivations and we will come to the conclusion. Yes, it is like that. It is not in the direction of E as you are thinking right now, that because of electric field it will be drifting towards the E, and it will be orbiting, and it will be like a spring kind of motion, or sometimes we will be saying it is a cycloid kind of motion, but it is absolutely not like that. Okay, so let us come to that interesting conclusion by making small derivations. We start with the vector equation. So you can see that I have not put any vector sign in any of these equations. You assume that the vector sign is there in all of them. So any vector, say v on the right hand side, whatever I have shown here in this one, any vector v, you can break that into two components, like here ud and v dash. So this is usually we are comfortable with, because we have done so much component division into this horizontal and perpendicular components like this one. But here this is a general one. So any vector v can be broken into two parts. One is ud and one is v dash. Suppose you are in a mood to fix the component ud. You want to split a vector into two parts, and one part you are deciding, okay, I will be making this part, this is my fixed vector. The other vector can always be found actually, because there are infinite number of combinations possible to compose a vector of certain magnitude and direction with different combinations. So if I am rigid about one component, the other component automatically comes actually, whatever the value. You are free to choose this value actually, okay. So then ud you have fixed, and this v dash come as per the requirement, and you get the vector like this. So here this equation was QE plus V cross B, okay. What I do actually, I split this V into two parts. One is V is equal to ud plus V dash, okay. And this ud is my choice now. What I choose, ud equal to E cross B by B square. This is my choice, okay. So nobody can say anything, because I have given a freedom to choose B dash. So accordingly B dash will be decided. One component ud I have fixed, and I will now put this V equal to ud plus B dash into this equation. Let us see what happens. So F is the force equal to QE plus ud cross B plus Q B dash cross B, because ud plus B dash I wrote there. Now ud, what we have done, E cross B by B square. That is my choice. I have put it over here, and what I am getting now, QE, I have got it over here, then 1 by B square into E cross B, okay. Now this is a step, this vector triple product, and here you must be very careful. That triple product, if you remember correctly, I am sure that some of you have already remembered that it is not in this form. You have to take into this form, okay. So you need to put a minus sign and take this B on this side, and you have to put this as B cross E cross B, okay. And then you are getting this term, you are writing it like this. Now once you are here, you know that you can split this into parts like E B dot B minus B E dot E. It is a vector identity, so I have just put over here. Now you know that this B dot B is nothing but B square, and then it is giving B square by B square, and then this cancels, then E minus C comes over here. And you see over here that B dot E, what is that? We choose this highlighted part, you see that we have chosen that E is perpendicular to B. That electric field is perpendicular to the magnetic field. So E dot B will be 0, okay. So that is how this term disappears, and this terms E minus E goes to 0, and what we are left with, Q B dash cross B. So what the equation you are now getting? F is equal to Q B dash cross B. Now you can understand what we have already warned you earlier, that whenever you are getting an equation of motion like F equal to Q V cross B, what you are going to get? You are getting simply a rotational motion, okay. Simply a rotational motion with velocity V under the magnetic field B. So here, what you have finally arrived that F equal Q V dash cross B. So it is a purely rotational motion of the charged particle of Q, mass M, with a velocity V dash surrounding the magnetic field B. Okay. So what we have done for that? So this V dash we have chosen, and this has come for a translational motion Vd is equal to E cross B by B square. This Ud is equal to E cross B by B square. That we have chosen. So this is basically composed of two motions. One is purely translational motion with velocity Ud is equal to E cross B by B square, that we have chosen, that is equal to Ud, and other is V dash, and with this V dash what it is doing? It is doing a just simply rotational motion. So what you have got now, the ultimate motion is basically a purely rotational motion with velocity V dash and a translational motion in the direction perpendicular to both E and V, and that is divided by B square, okay, the velocity magnitude, okay. So what you are seeing that the particle is now drifting in a direction perpendicular to both E and B, and simultaneously it is making a rotational motion surrounding the magnetic field B with velocity B dash. So ultimately some features of this particle kinetics under the uniform E and B field, what you are getting a constant velocity V dash, V perpendicular parallel to B. Gyration around the magnetic field with radius RL equal to mv perpendicular dash by BQ. And a constant deep velocity ud equal E by B at right angles to both E and B field. The drift motion is independent of sign of the charged particles. So that is very interesting actually. The drift motion is independent of the sign of the charged particle. So whether it is positive charged particle or it is a negative charged particle, it will be drifted in the same directions. And the other important thing is that the drift motion is independent of mass of the charged particle. See, the drift motion is E cross B by B square. Okay. So if it is E cross B by B square, it is not having the mass in that. So the drift motion is independent of mass of the charge. So what you can conclude at this point is that all components of the plasma drift along together even though their individual gyration may be vastly different. So at this end, what we are getting that under the case when electric field is perpendicular to the magnetic field, the particles move in a direction perpendicular to both E and B field. Here actually we have got the solution of the equations. I have just solved those equations and we have got this thing. You see that the electric field is in the y direction and B is in the z direction, and the particles are rotating. You see that the particles are rotating and moving in a direction to both E and B. The when your electric field is more, the movement is faster and you are making a sharper and sharper loop, as we can see here. So I have just increased the electric field from 0 to 0.1 to 1 to 3, and how the motions are changing over here. So in our next class, what we will do actually, we will go for the case when electric field is 0 but gradient of magnetic field is not 0. We will get some very important conclusion in that. So I stop here in this class. So in the next class, we will go for the plasma kinetics for the case when electric field is 0, magnetic field is not 0, and there is a gradient in the magnetic field. So gradient in the magnetic field plays a very important role in plasma behavior, in devices. It is very necessary and important to understand those configurations. So we'll study that in the next class. So thank you.